so we'll try to be nice to you. Okay, thank you, Feder. Okay. So I wasn't supposed to give any more lectures, but they kindly let me to give this little last remarks here. And if I can find, I wanted to show you the SurveyMonkey survey for my lecture. Where is it? Many tabs here. Oh, here it is. Okay, so I was up at 4:30 and giving a lecture to you, and it was couldn't see your faces. It's so much nicer to see your faces. And I was talking about are people Bayesian? You know, how do people learn versus how do machines learn? And it's good because it also helps you learn, because it helps me learn, because it's simple pedagogy. You know, we're using neural nets. We're very simple ones, and I'm using them in MATLAB. And I put some Feder put my software in MATLAB onto the Dropbox, and I'll show you some of the results. But here's some results that we started and gave you the survey. Remember that, you know, if you were there at the lecture, Are People Bayesian was an experiment they did with human subjects, and they had 2 bingo cages. And there was a 3rd bingo cage that was like the prior cage, and it determines whether you choose cage A or B. Cage A had 4 balls marked, both of them had 6 balls. Cage A had 4 balls marked N, 2 balls marked G, so it's 2/3 probability of an N ball. That's the ball of interest. And then cage B had 50-50. And then we showed you a sample that was drawn. So there's the prior cage. So if one of the cages gets selected with a probability of 2/3, well, that's the cage A is selected with probability 2/3. Doesn't mean it will always be selected. And then so you don't see which cage is selected, but you see the draw, and there was N, G, G, N. So there's 3 N's and 3 G's. Well, that's like cage B. And of the 14 people who responded, they said, yeah, it must have been from cage, most likely been from cage B. But the right answer was cage A. That has a posterior probability of 58%. So if you go through and calculate it, so this is all anonymous, so we're not tracking who said what. Right? But just shows you this is a sophisticated audience interested in learning, and you see that it's learning. Just a simple learning test is not trivial. Okay, so humans aren't perfect, but we're actually pretty good. You know, so in some sense, although we criticize and we find failures in rationality, when you think about all the things we have to learn and the different things and the different mechanisms, it's pretty amazing what we actually do. Now, I want to just show you the software and some of the graphs that I showed you. I'm not going to go through all of them, but I have a README file, and it describes the programs you can run. So one is called Classify Subjects. Remember, I talked a little bit about the EC algorithm and different ways of handling heterogeneity to discover different types. So you thought of that as unsupervised learning, and then to estimate the El-Gamal cutoff rule, El-Gamal, and then what I call the structural logit model, which I showed you has an interpretation of a simple neural network with 2 inputs and 1 output, 2 layers. So it's got a depth of 2 and a width of 1. And so if you run the program, let's do that. This is just to show you that it runs, and I'll just point out some results that you can look at. There it's using the MATLAB neural network toolbox to actually fit this neural net. And then I have my own, a hand-ruled way of doing it. And I just want to show you that. And then these are all some of the graphs that come out of it. There's like a total of 10 graphs that pop up in it. I showed you many of these already, so I'm just showing you these. But remember that, you get these 2 types, and it discovers a type 1. And if you're perfect Bayesian, it's the dotted line. So if your posterior probability on this axis, the true posterior probability, this is the fraction of subjects who choose cage A, and there's this black line. That's just the data. The non-parametric fraction of the subjects at each of the possible posteriors in the data, indicated by the true posterior. And it really, you know, the red line are the ones that are more Bayesian. That's 63%. And then the blue line are the other people who are less Bayesian, less rational. Because a perfectly rational person will follow the dotted line, right? And if you just have a belief that's even slightly over 50%, you should choose KJ. Okay, so you have all these graphs. And what I want to show you is the network toolbox. How many people have used MATLAB's network toolbox? Yeah. It's actually an easy entry point into learning these, and you can design nets. It's got its flaws, and you know it's not perfect, and probably the one in Python, TensorFlow, much better. But for somebody like me, an old guy, it was an easy way to get into this and to see and play with them, right? So play with them in a simple model and see how they perform. Now, one of the key other results I point to is that in my subjective Bayesian structural logit model, we can uncover, like, so that's what, you know, as a student of Dan McFadden, it's revealed preference, right? You see people's choices and you try to, you know, go backwards and uncover what's in their head. And what we get is a subjective posterior belief. And if they're correct, they should be following the, if they're perfect Bayesians, they should be on the 45-degree line. That's being a perfect Bayesian in your beliefs. And what we see is the subjective beliefs reflect overconfidence, right? If you believe, if the true posterior is below 50%, they think it's even lower than that. They're more certain that it's either cage B or cage A, depending on the true posterior. So you get that result. And well, let me just point out some things, though. We can quantify here the loss. If you're a perfect Bayesian, the payoff, if you were going to get $1 in this experiment, if you got the right answer, you get 69 cents on average if you followed Bayesian rule perfectly. Now, the subjects in this, if you believe our structural logit, they're going to get 64 cents. So that's the cost. They're sacrificing 5 cents with their human fallibility, but not bad, right? Now, if you think about, if you use El Gamal and Grether's model, it reflects more suboptimality, 62 cents they would get. So you can quantify and you think about what's the loss in terms, and we showed that Bayes' rule was the best way to make a decision. Well, I didn't show it, but that's just an exercise in probability theory to show that that's the best way to make a decision if you're just greedy and you want to make as much money as possible. Now, I just want to show you kind of a geeky thing I'm a little bit proud of, but you know, I'm estimating my own neural net. I wouldn't call it a neural net, you know, but here's what MATLAB does, and they're using the cross entropy, and it kind of annoys me, but that's just the negative log likelihood. And so, you know, I wanted to verify this is the coefficients that come out of it, and then here I run my own algorithm, and if you look at the log likelihood, it's you know, you translate the negative log likely and put it in, and it's an average. So if you put it back in my terms, that for all the subjects, it's minus 1768.99. Now, I run mine, and I beat it. I get 1762. So, and what you find is you run the MATLAB every time is different because it's using stochastic gradient descent, and it gets stuck on local optimum. Whereas I'm using just good old BFGS, and it seems to find almost always a better result than MATLAB. So you might say, well, MATLAB is, you know, I don't want to say it's junk or anything, you know, but it's just using, you know, it's introducing stochastic gradient descent, and what happens is, you know, it gets stuck up, and that's one of the problems of these neural nets. And then, you know, here's the parameters. Here's the MATLAB, and they're pretty similar here, you know, but here there's some big differences. Now, another thing I'll point out is you won't get standard, these are the standard errors of the parameter, and we use, you know, the good old inverse of the Hessian. That's how we get standard errors. Try getting standard errors out of a neural net on MATLAB. I don't know, does anyone know how to do that? I mean, it's using, you know, backpropagation is calculating recursively gradients, but nowhere does it actually produce standard, you know, the variability of the parameters. And I guess it's just the mentality is, you know, engineers don't care about the standard errors, but econometricians do. Try publishing a paper if you don't have standard errors in your parameters, and it's better to have an interpretation for them. Okay, now the next program I want to just run is, it's called counterfactual. Now, this is what I didn't really get to. This is really one of the most important things why we do structural econometrics is that we want to do counterfactual predictions, right? And so I'm looking now at another paper that Elgamal and Grether wrote. It's called Changing Decision Rules. It was another experiment that they conducted while Mahmoud in 1999. He was at the University of Wisconsin so the first one was done in California, the second one was done in Wisconsin. And now what they did is they did two experiments. On successive days, the first day, some of the subjects did the California one, exactly like the one I said, 6 balls in each urn. But they were worried about this idea of lock-on, easy, like we talk about type 1 and type 2, decision rules where it was just easy. You say 3 and 3, that sample looked like a cage B. I'm just going to choose cage B. That's your system 1 in Tversky language, right? Just take the knee-jerk, easy answer without thinking too hard about it. So they wanted to kind of make it harder to use what they call the representativeness rule in psychology. So they had a second day, the same subjects came back, and were facing now cages with 10 balls, and they were drawing 7 balls with replacement out of cages with 10 balls in them. So now instead of 6 balls, there's 10 balls, and instead of a sample of 6 out of a cage of 6, there's 7 balls drawn with replacement out of a cage of 10. And 7 was chosen because you're not going to get 50-50 anymore. So, the two cages, one had 40% ends, and the other had 60%, 4 out of 10, 6 out of 10 in these two cages. So then the question is, this is a kind of a simple counterfactual. Can we use, if we observe the subjects and estimated their decision rule based on day 1, how well would it predict, how well could we predict what they did on day 2, right? Okay, so what do you think? Do you think day 1, is it such a change? It goes to 6 to 10, is it that big? I don't know. Do you think their behavior would change radically or not? What does anyone think? Is it going to have almost no change, or could their behavior have changed by this experimental design? Well, you don't know, but let's show you what happens. I'm going to run the second code called counterfactual prediction. And what it's going to do, it's another MATLAB code that's going to actually show you different models. And again, it's running the deep net toolbox with not such a deep net, two layers. And it's doing all the calculations in real time. And then it's going to put up some graphs. Okay, so now let's go on these graphs and let me show you, first of all, the data. And then I'll show you the models and what they do, because there's going to be a little bit of a surprise here. Okay, so let's show you the first one. This is the data, and the blue line is day 1 with 6 balls. And then here it's again plotted with a true posterior, and if subjects are truly Bayesian, they should follow the dotted line. Now day 2, it's the red line. But by and large, I would look at that and say, well, including the standard errors, they're not that different. The behavior didn't change that much. Okay, they both, they're kind of noisy Bayesian, and maybe on day 2, the day 1, they're a little bit closer to Bayes' rule. This is a little bit closer, and then up there it's a little bit higher. But basically behavior didn't change in a radical way. Now let's see what would happen if let's just see what the models predict. Now here, first of all, we estimate in the training sample on day 1 with the 6 balls, we estimate 2 models. The red line is the neural network with 5 parameters. The blue line is my structural logit with 4 parameters with a structural interpretation and standard errors and the whole 9 yards. And you see the predictions are almost identical, and they're matching the data pretty closely. Okay. Now we want to do counterfactual. We estimated these two models. Now I'm going to take them and apply them to day 2 when there's 10 balls, 7 balls drawn out of 10. Which model is going to do better? Well, let me show you. Here's the neural net. It's going crazy. Gone crazy. The structural model isn't perfect. The black line is the data, and the blue line is getting much closer to the data. In other words, the structural model predicts the no change in behavior much better than the neural net, which has gone completely haywire. Now, you might say, and I checked this, did I make any programming mistake or anything? Now, what you can do is, just to make sure this neural net is really, did I get stuck on a local optimum? I go and re-estimate the neural net on the evaluation sample. Okay, so the blue line now is I fit this same architecture, neural net on the data. It actually looks like the data. It's capable, but the day 1 parameters are just not relevant for day 2. Okay, so why does the neural, now we talked about some people at the Resources for the Future were claiming that they could use machine learning to do counterfactual prediction. Well, I'd say it's still an open question. I was worried. I created about my own angst. Am I going to be irrelevant? Is a machine going to replace me? It takes me so long to write these structural papers and do these counterfactual predictions. And if a machine will do it like that, I'm out of a job. But I think that my job is still safe for a little bit of time. We have to come to the bottom of why is the neural net doing badly in the counterfactual prediction, even though if you look at it in all criteria, likelihood and everything, it fits really, really well in the training sample, but it goes haywire in the outer sample. Now, so let's just throw out some possibilities. Does anyone have any conjectures? Why does this do badly? Do you have any insight? Why would the neural network do badly in counterfactual prediction? Yeah.
The parameters in the neural net are not economic parameters. In other words, the machine really has no idea what's going on. So it's just trying to, go down the local maximum or whatever. But if the structure of the problem has changed a couple periods later,
that's kind of, that's getting closer. Yeah.
Another way to phrase this is that you can impose certain structures over the problem and still apply a neural network, right?
Yeah. The structure is kind of a neural net, but it's built in a theoretical thing that comes from the human, the understanding.
Yeah.
And
sorry, but I mean, if you have an estimate, like you can phrase it in some sort of statistical estimate, then you might be able to back out some. You map the neural network down to some low dimensional projection of what you want to solve.
That's right, and that's what my structural logit model does. It's like a neural net with a structural interpretation, and the key parameters there was a parameter on the likelihood ratio and the parameter on the log prior odds ratio. Those are two. Remember, I talked about the structural model depends on transformed inputs, but a neural net only so there's two key inputs. The prior, we'll call it pi, and the number of balls marked n called little n. Pi and n. Now, my structural model transforms those inputs and uses those as the covariance, the log likelihood ratio and the log prior odds ratio. The neural net, I just put in pi and n. Now, right away, you see, because n can only go from 0 to 6 when there's 6 balls. You can have 0 balls marked n up to 6. When you have to draw 7, it goes from 0 to 7. Now, you say there's a lot of overlap. There's only one more ball. But there's something very different I'll show you in a minute. The log likelihood ratio is downward sloping in one experiment and upward sloping in another. It's a huge change that the neural net just doesn't get. It just putting in n and pi, it doesn't realize that the log likelihood ratio has flipped because of the probabilities on the cage, and that's just throwing things backward. Now, I'm going to show you that the neural net can be redeemed if we transform the input. So if we estimate this 5-parameter neural net with the transformed inputs, then things work well. So let me show you that. And how much, I go to 4, or what time do I have to stop, or should I stop now? I won't go too much longer. I'm not gonna, Jeremy, we're gonna talk 4 minutes? 4, okay. All right, we'll see what we can do, but I'm going to now, I'm going to change an input here, transform inputs. It's, I'm not transforming them, so I'm just putting in pi and n. So now I'm going to go down here and I'm going to transform the inputs, just like I do in the structural model. So you might say now they're even Steven. This is not what an average person doing neural nets would do, though. They wouldn't think to why transform the inputs, you know? But this is what the human does when you're thinking about Bayes' rules, specification. Now, at least this human thought about this. So now let's see what happens if I do the same thing now. And going through the same thing. Estimate the neural net, now 5 parameters now with transformed inputs, not just the regular inputs. And boy, it's taking a long time here. MATLAB is, you know, churning out. The stochastic gradients, you know, mine's have already finished. MATLAB's going kind of slowly. All right, so now let's show you. Yeah, here it is. Let me get rid of this toolbar. This is it was figure 3. Where's, yeah, here the red line and the blue line, they're almost identical. Almost identical. And now we get, you know, the neural net with the transformed inputs. Now, so what's happening is, you know, you can think about what people do. They're just not looking, you know, they're doing something smart. They're like evaluating the likelihood ratio and the log priority ratio. Some put different weights on them, but they're thinking both information and they're thinking more in terms of likelihood ratios, not just n and pi. So when you train it, a neural net, without thinking about that transformation of the inputs, it is compromised from the start. It's compromised in terms of its ability to do counterfactual prediction. Now, you can solve that. We talked about adding another level to the neural net, or another, you know, you get a 3 level or 4 level. You put in n and pi, and then you train it to get the log likelihood ratio and the log prior odds ratio. And you can build neural nets that do that. So let's just show you a simple one using the MATLAB software that can do that. And so, in other words, I need a deeper net. So what I would do is called, let's see, where is it? Log posterior, I have a command called log posterior learning. And what this is going to do is, it's like the first 2 stages. Oops. What's going on here? Oh, let me clear. Something is messed up in memory. Clear all. Now let's try it. It was working just a minute ago, but all right. Well, the point is that you can put more levels on you build a deeper neural network, and the earlier levels discover, essentially, if you're training the neural net, the other levels discover the log likelihood ratio and the log prior odds ratio. And then in this deeper neural net, which will have far more parameters, I need 31 more parameters to train just the log prior odds ratio. Maybe not as many to do the log likelihood ratio, but with those additional layers now, I have like a 4-layer or a 3-layer neural net. Then it can essentially discover Bayes' rule. Okay. Now the question is how much training so now we go to the idea is maybe the human is like a machine learner. Let's just entertain that possibility. We are deep neural nets ourselves. So how many observations? So the thing that's cool about humans, we don't need a billion observations to do well something. We only need a few examples, and we can generally get it quickly. You do a few examples, and then people somehow get like tie your shoe. You remember when you had to tie your shoes? Like how many? You didn't have to tie your shoes 1,000 times to learn how to tie your shoe. You saw a few examples. You got it wrong a few times. But after 3 or 4 times, mostly, you'll be able to tie your shoes, right? So that's what's different. But machines need lots and lots of data. So, but let's just see, let's give the machine limited data. And yeah. No, go ahead.
So we were talking about this during lunch, like comparing like human trials and Dr. Jason, like tax dollars and get it versus a machine learning. And the question we were wondering was how much of that is your training, right? You're born with some kind of.
You're built, yeah, with onboard physics knowledge, yeah. Yeah.
This is an old argument in language learning. Noam Chomsky said we have sort of a language instinct, and the reason children learn languages so fast is they have sort of a built-in apparatus that is ready for you to learn the language, and you learn way faster than a deep language model learner.
Yeah, but let me give you an example of how good the neural nets are now. I was just reading an article. I put it in the Dropbox. An article in Nature. Now they have, there's been people who are paralyzed or blind, and there was a really great example of a person who was blind, and they put this device on their tongue, which is like a image from a camera that gives your tongue little shocks when you stick out your tongue. It translates the visual images into little shocks that you can feel on your tongue. And when you're trained enough, the human deep net starts to look at this as vision. And blind people can walk around and perfectly fine. They're sticking out their tongue, and their tongue is relaying images that their brain trains to see as like sight.
Yeah, it's not only that, they can actually see it localized in the visual cortex. So their tongue gets mapped.
It's like they don't need
eyes
like
being mapped.
Exactly.
Your tongue gets mapped.
Now, the reverse is this article in Nature came out just this week. It's a woman who was paralyzed. She had a stroke in her brainstem in 2005. And she lost the ability to speak. The brainstem, you have the higher cortex. That was fine in her, was right down in the brainstem where the nerves come, which can affect your ability to move your tongue and vocalize and talk. So she could think perfectly well, but she couldn't talk at all. So what they did is an operation is pretty incredible. They kind of took off part of her left skull and put a bunch of electrodes, like 253 electrodes, deep wired to the cortex of because basically the thoughts of how you make a sentence are done at the higher level, and then they're relayed deeper into the brain. So then they have a wire coming out of her skull, and then with those signals, they trained a deep neural network to recognize the individual words. So for 14 days, she would just think sentences, and the neural net would see these signals, and then she had an independent way of saying what she was trying to say. She had a slower method so they could see as they were doing supervised learning, and the neural net after 14 days could learn within a matter of seconds she just thinks, and then on a screen, it not only types it out, but it vocalizes, and then they have an avatar that actually has their facial. So they trained it not only on the speech, but on the facial expressions, so that it's like talking to a real human being who can't move their face, right?
So Wittgenstein has one of the most compelling things he says in philosophical investigations is that if you give a person a wooden spoon and you ask them to sort of touch a surface, and you ask them, how does it feel? They don't tell you what it feels like on your fingers. They say, I can feel that as being rough or smooth. The way you feel it, rough or smooth, with your finger. So that maps your brain is mapping whatever it receives from the object
Yeah.
into your brain part that perceives roughness.
Yeah. And so it's just totally cool, so the point here is, there's really deep in, about what consciousness is, there's a Google guy got fired because he was convinced that now these like ChatGPT, that they are conscious, and Google didn't want him saying that, and they said, and what level of awareness where we start to get emergent properties like, Bertel was telling me, he fed his final exam into ChatGPT and it like completely nailed, he was like flabbergasted. He thought that ChatGPT could never answer his final exam in structural econometrics, and yet it kind of like the least first two questions, it just nailed it, right?
There were 7 questions and nailed all of them, including the data analysis of the data set I provided. Of course, I had to like give it, just ask it to write a Python program to do whatever was asked in this PDF.
Yeah. So the bottom line of all this is, you have to take notice of all this, and some of the training is not, billions of eons and epochs to train these machines. Now, what I'm going to do now is take my simple neural networks, the structural one and the non-structural one, and I'm going to train them on only 20 instances and see what comes out. So in other words, it's like you have a supervised learning and they're presented random pi and n drawings. And then the answer is a perfect Bayesian would say either cage A or cage B. They're not told what cage you actually draw. It's just what a perfect Bayesian would do, right? And so it'll calculate the posterior probability. If it's less than 1/2, it'll say cage B. If it's greater than 1/2, it'll say cage A. So now we're going to train these trained neural nets and see how they behave. So it, really fast, the models have 5 parameters and okay, so this is 20 observations. So take a look at this. This is 20 observations. It's behaving almost like the blue line is the choice probability. And there's the dotted lines, perfect Bayes rule. After only 20 observations, this machine is behaving almost like a perfect Bayesian. And its revealed beliefs, the red line, are almost on the 45-degree line. Its revealed beliefs are almost like that of a perfect Bayesian with very limited observation. So now you might say, are people Bayesian? If we're not really trained in Bayesian, if our deep net would just see some examples, a limited number, could our brains just intuitively train without knowing any Bayes rule, right? And this goes back to whole, idea about rationality, like Milton Friedman, right? So Rick's from Chicago. There was debate between Herb Simon and Milton Friedman. Herb Simon would say, well, there's bounded rationality, right? And people, can't possibly solve these dynamic models. They're too hard, all these learning statistical problems. And then there was Milton Friedman say, well, it's as if, in other words, they practice and they play in their brain. It's like you can play pool and you're using a lot of physics. Angle of incidence equals angle of reflection. FT equals MA, if I remember my physics and everything, right? And they just learn it intuitively, right? And so maybe Friedman is right?
Myron Minsky said that the amazing thing about the sort of differences between computers and people is that the easy things are hard and the hard things are easy. So computers can do these amazing calculations that we humans are like, how in the world can it do that so fast? So things that are hard for us, the computer finds easy. But the things that are easy for us, like I can see that's John Rust over there. It's taken, only finally now with millions of processors.
Yeah, I agree with everything you're saying. So it's at 4 o'clock. I just want to conclude though. Right now, a machine that was trained on only 20 observations is not a good. It's better than human already, right? Because we saw the humans, their choice probably wasn't this close to Bayes rule. We're much farther away. There was much more noise in what we're doing. So you might say, wow, a machine, a simple neuron with only 5 parameters, a simple neural net is actually outperforming these human subjects. We have much, what's wrong with us, right? Does this spell our doom? But let me give you some final saving grace for the humans. They weren't trained, right? This got 20 training examples, but in Elgamal and Grether, There was no training. There was no feedback until the final end of the experiments when they got a paycheck on the numbers that they got right. But, you know, between day 1 and day 2 in the Wisconsin, there was no feedback at all. So how would you train a neural net if you didn't have any training observations at all? So what's happening is, you know, that's intelligence. They're thrust into a new domain, no training, yet they can behave intelligently. And so how do we do that? How do we do something well with no training at all? Yeah, Chris.
Professor, just to give humans a little bit more of grace compared to the artificial neural nets, we burn far less energy.
Yeah, well, you're right. And that's a very good point. I always make that point. Our brain uses about 10 watts of energy. You know, if you think of all the computers that were used to, you know, train AlphaZero, they're probably using, you know, thousands of watts, watt hours to train in about 4 hours, but they probably had, you know, 500,000 machines working to train this farm. So yeah, there's some really impressive things. And you say we're lazy, there's good biological reasons. Our brain is lazy because we're conserving energy and we're trying to use knee-jerk reactions. And if you think about this experiment again, the rewards weren't very big. If you would have said you get $1 million for picking the right thing, probably people would have, you know, the errors would have been much less. So I'll just stop there and say, we still have a chance, human beings. We still have a chance.